Lesson 3.2 is all about linear functions. So a linear equation is an equation that uses x and y and can be written in the form, and this should be familiar, y equals mx plus b. M and b in this situation are constants. That means they should be filled in with numbers that don't change during the course of a specific problem. Linear function is ever so slightly more specific. A linear function is a non-vertical line. A vertical line has an undefined slope. It's not considered a function. That's something we would have looked at yesterday in 3.1's lesson. So linear equations, linear functions have a constant rate of change, which we always often refer to as slope. We'll often call it slope, but rate of change is the same idea here. So when identifying linear functions from a graph, it has to be a non-vertical line. All right. So this one does not work because it's not a line. It's not straight, so it's not a line. This one does work because it is a line and it's also not vertical. It's a non-vertical line. So this one is linear. And this one is not linear. And that's all the more simple the reasoning is for these. If you see a graph, it should be, it's a line, it's not a line, right? And then the only iffy situation is if it's a vertical line. Yeah, it's straight, but you can't call it a function, all right? So these are both functions, but this one's nonlinear because it's not straight. Another common type of problem you're going to see here is if I give you a table of values, can you tell if it's linear? All right, what we're looking for is a constant rate of change. So slope is often written delta y over delta x. That means change in y over change in x. Change in y over change in x. So my expectation is that you check every single pair of points. X goes up 3, 3 to 6 is 3, 6 to 9 is 3, 9 to 12 is 3. So we do have a constant change in x of plus 3. And then the y, let's check the y. 36 to 30 is minus 6. 30 to 24 is minus 6. 24 to 18 is minus 6. So what I do is I put my y change over my x change as a fraction. Negative 6 over positive 3. And I can simplify that. Negative 6 over 3 is the same as negative 2. Now, if we are able to find these constant changes, it's linear. It has a constant rate of change. This is the vocabulary I expect us to be able to use and understand for problems like this. Let's look at one more that doesn't work out. Here's another table, and we're going to analyze it the same way we did the last one. 1 to 3 is plus 2, 3 to 5 is plus 2, 5 to 7 is plus 2. So the x looks constant. Cool. 2 to 9 is plus 7, 9 to 20 is plus 11, 20 to 35 is plus 15. All right, so that is not constant, which would make this nonlinear. It can still be a function, but this one is going to be a nonlinear function. All right, so that would be in some way curvy on the graph. Here's where we start to get into some math that I'm going to consider a little bit more challenging for us. All right, to figure out if these are linear or not, our goal has to be getting everything into y equals mx plus b. If we are able to do this, if we are capable of getting it into that form, it's a linear function. Okay, now let's talk about what we don't see in here. All right, when we try to get y by itself, x should not have an exponent. X should not be square rooted. X should not be in the denominator. What else? Ooh, up here we see one. Not in the exponent. We don't even know how to handle that yet. So of course we're not going to call it linear. Okay, so let's try to break these down. This is kind of what we're trying to look for. So immediately what I want to do is I want to recognize this has an x squared. All right, that is not going to be linear. Up here, x is square rooted. This is not going to be linear. This one has x in the exponent. That's non-linear. Okay, the rest of these already have y by themselves. This one, x is in the denominator. That's non-linear. There's no way to get that in the numerator and keep it away from the y. Okay, so following these rules is just an at-a-glance way to decide if something's linear or not. But now we have to break apart these other two that we haven't gotten to yet and make sure we know how to decide, because they don't have those same issues. But let's make sure they still work. All right, so no square roots. X shouldn't be in the exponent. X shouldn't be in the denominator. X should not have an exponent with it. But these don't have any of those issues. How can I rewrite this so it's y equals mx plus b? X is just missing. So a neat little math trick I can do, some mathematical aerobics. What 0 times anything is just 0. So I can always put a 0x if I don't see an x. We can always do that. And then we had a positive 3.8, so I'll just add 3.8. This is now mx plus b. Yes, m is 0, but that's fine. 0 is a slope. This would be a horizontal line. So this is linear. And down here, well, I'm going to distribute to get rid of those parentheses. And now it immediately looks like y equals mx plus b. All right, so this one again is linear. Oftentimes, if we don't see those issues I talked about, it's going to end up being linear. These are some key things to look for that are going to end up curvy as a graph. We have a new definition for solution for this lesson as well. The solution is no longer a single number. We are now looking for an xy ordered pair, a point on a graph that makes the equation true. If we get all the solutions and plot them on a graph, it'll form a line when we plot those points. Okay, so there is no longer a single solution, but if I'm given an x value or a y value, I should be able to find its partner that's a point on my graph. We're not really going to be finding those right now, but understanding this is the definition of solution when we're talking about a linear equation like this. We have two types of equations too, or two types of solutions. Discrete is often when we don't want to use decimals or want to limit ourselves in any way. Discrete we talked about, this looks like individual points plotted. While continuous is actually the full connected line. This is when we want every piece of information. Okay, so continuous is really good for like a physics situation, because when something's moving, it's not skipping spaces so that it doesn't use decimals. It moves in a nice smooth motion. Discrete, on the other hand, like if we're talking about, I don't know, dollar amounts, all right? Dollars only go to 2 decimals. So between $1.11 and $1.12, there are no decimals in between. We don't use half pennies. So that would be individual points. Yes, I'm using decimals, but I'm still limiting myself in some way. We only go to 2 decimal places with money. Money really is a discrete value. Now, insurance companies and banks will go a little bit more precise with it, but we don't treat money like continuous all the time. Sometimes we treat money like discrete when we're looking at specific dollar amounts, or if we're looking at how old someone is and only collecting their year age. All right? Age is a continuous thing, but if we're only looking at how old someone is by year, we might just take that whole number year. So discrete is sometimes used when we're collecting data. Continuous, oftentimes in science, is what's used because we do care about those in-between fractions and being precise.